Hi guys, I'm Aryan Agarwala. I'm a 6-star programmer on CodeChef and a master on Codeforces. Welcome to our channel, Learn Competitive Program with CodeChef. If you want to master algorithms and data structures, then this is a great resource for you. Every week, we upload solutions to problems on CodeChef, tutorials on various programming paradigms, and even conduct live problem-solving sessions. So here's a reminder to make sure to subscribe and hit the bell icon for notifications. Hi guys, I'm Aryan Agarwal. Currently, I'm a 6-star programmer on CodeChef and a master on Codeforces. Welcome to our channel, Learn Competitive Programming with CodeChef. If you want to master algorithms and data structures, then this is a great resource for you. Every week, we upload solutions to problems from CodeChef, tutorials on various programming paradigms, and even conduct live problem solving sessions. So here's a reminder to hit the subscribe button and click on the bell icon to stay notified. Today, we're going to discuss a problem named communication channel. This is a medium level problem, but I think it's closer to easy medium personally. Um, for this, the topics you'll need to know beforehand are divide and conquer DP optimization and probabilities and expectations. I'll very mildly cover both of them in this video itself. However, I strongly recommend knowing both of these as a prerequisite. Now, let's look at the problem statement. So the problem says there is a communication channel with n plus 1 stations numbered from 0 through n. Okay, so the stations are numbered 0, 1, all the way to n. Station 0 wants to send a message to station n. Now, you may install memory disks at up to k of the stations between 1 and n minus 1. So you need to select k stations and install memory disks at them. Okay. Um, Now let's denote the increasing sequence of stations at which memory disks are installed by V1, V2 all the way to Vk, um, where small k, which is the number of memory disks you install, is less than equal to big K, which is given as input. Okay. Now V0 and Vk plus 1 are 0 and n respectively. What this means is that there's already a memory disk installed at station 0 and station n. Okay, that's why we're only selecting between 1 and n minus 1. Now, in stations that don't have a memory disk, it's only possible to send the message forward without storing it for later. Let's see what this means. So, for each I between 0 and n minus 1, if the message is currently at station I, then the station can send the message to station I plus 1. So the stations are connected in a chain where 0 is connected to 1, 1 is connected to 2, and so on and so forth. Now, this transfer between adjacent stations takes 1 second. Okay, and there is a chance of failure of this transfer. Okay, like there is a chance that you may try to transfer from I to I plus 1, but for whatever reason the transfer fails. Okay, regardless of whether it fails or doesn't fail, the transfer takes 1 second. Okay, and the transfer succeeds with probability pi and it fails with probability obviously 1 minus pi. Okay, now our task here, sorry, if the transfer fails, then um, it's not like you can do the transfer again immediately. Okay, so if the transfer fails at station I, then it goes back to station J, where J was the last station with a memory disk. Okay, so let's say memory disks are at station 1 to 10, 11. Okay, and you were trying to do a transfer from 9 to 10. Okay, then if that transfer fails, then it doesn't go back to station 9, it goes back to station 2. Okay, the last one which had a memory disk. Okay, so we need to choose k stations such that if the memory disk is installed in those k stations, then the expected value of time needed to deliver this message all the way to station n is minimal. Okay, so we're using this expected value concept, which is a part of probability theory. Now, one more thing is, you are not actually given the probabilities directly. This pi is not given directly. Instead, it's you're given a non-integer, non-increasing integer sequence, f0, f1, all the way to fn. And for each valid I, you can calculate pi, which is the probability of success from transferring from I to I plus 1. You can calculate that as f of I plus 1 divided by f of I. Okay. So, for example, probability of 1 will be f of 2 divided by f of 1. Probability of 2 will be f of 3 divided by f of 2, so on and so forth. Okay. So let's look at the constraints. Okay, so T is it's a multi-test case format. So T is between 1 and 10 to the power 5. N is also between 1 and 10 to the power 5. So that means it's looking for a linear or close to linear solution. K is very small. Okay, so K is between 0 and 50. So that means it's a big hint here. So that means order of N into K will also pass. Okay, and finally we're given this extra constraint that f is between 1 and 10 to the power 12, and of course like we saw above, f is non-increasing, it's decreasing. Okay, um, so let's look at what the sample input is saying. Okay, we won't solve the sample input because you need to study a bit more before you can solve it. There's a single test case with n is equal to 2 and k is equal to 1. Okay, and there are obviously three nodes, 0, 1, 2, and f of 0 is 4, f of 1 is 2, and f of 2 is 1. Okay, now we can see that the probability, the orange arrows and the values above them represent the data transfer from the nodes and between the nodes, sorry, and the value above them represents the probability of success. Okay, so we can see the probability of success from transferring from 0 to 1 is equal to f of 1 by f of 0, right, which is 2 by 4, 0.5. Similarly, from 1 to 2 is equal to f of 2 upon f of 1, which is 1 by 2, 0.5. Okay, now we'll solve the sample test case later. I mean, we'll implicitly solve it while we're learning how to do it, because there are a few things that are not so obvious. Now, the first thing we need to understand is expected time. Let's define a function t over two variables u and v, where u is less than v. Okay, and what this function means is the expected time taken to reach station v from station u. Okay, so if we have this in a problem, will get much easier. So how do we calculate this? Well, here are some ideas. The first observation is that okay, this is like sort of a derivation that will make the rest of our work very easy. So let's look at what this means. Okay, so from I is equal to 0 to v, okay, we're doing this, this is just a term, like a multiplication term. So this means like pu multiplied by pu plus 1 plus in multiplied by pu plus 2 all the way to p of v. Okay, we want to find an easier way to represent this, okay, because we'll be using this term quite a bit. Okay, so notice that we can reduce this to, not reduce this, we're just replacing pi with f of I plus 1 upon f of I, right, the definition as per the problem statement. Okay, and so let's expand this here as we've done on the left. Okay, to f of u plus 1 upon f of u into f of u plus 2 upon f of u plus 1 into f of u plus 3 upon f of u plus 2. Okay, so on and so forth until f of v plus 1 upon f of v, right? Now notice that these terms are quite similar. F of u plus 1 appears in the numerator and then the denominator. Same for u plus 2, and same would be true for u plus 3 if I had written more terms in the middle. Okay, so we can keep on cancelling these terms until all we're left with is f of v plus 1 upon f of u. So we have that the product of the probabilities from u to v is equal to f of v plus 1 upon f of u. Okay, this is our first observation, it's very important. Now, to calculate t of u and v, let's calculate the expected time of each edge individually. Okay, so the data is passing from u to u plus 1 via the first edge, then u plus 1 to 2 via the second edge, then u plus 2 to u plus 3 via the third edge, so on and so forth until v minus 1 to v, okay, minus the v minus uth edge. Okay, now, the first edge connecting u and u plus 1 will definitely take 1 second, right? Regardless of whether we have a success or a failure, right? Therefore, its expected time will be 1, which can be written as f of u upon f of u. Okay? Then the second edge, which connects u plus 1 and u plus 2, will take 1 second. However, this is assuming that the first transfer is successful, right? Only if the transfer from u to u plus 1 is successful can you travel the edge between u plus 1 and u plus 2. Therefore, the expected time for this will be 1, which is the time, multiplied by the probability of us reaching it, which is p of u, which is f of u plus 1 upon f of u. Okay, and you can see why we wrote 1 as f of u by f of u earlier, so that we have the same denominator for everything. Okay, Now similarly for the third edge connecting u plus 2 and u plus 3, okay, that will also take 1 second, and using the same concept, we'll only travel this edge if the first two transfers are successful, right? Therefore, the expected time for the third edge will be 1, which is the time, multiplied by pu plus 1, okay? And using our formula, like the product of pi from u to v is equal to p v plus 1 upon pu. So, p of u multiplied by pu plus 1 is equal to f of u plus 2 upon f of u, right? Setting v as u plus 1. Okay. Now, if we keep on expanding this all the way to the v minus uth edge, then we'll get this. Okay. F of u plus f of u plus 1 plus f of u plus 2 all the way to f of v minus 1 divided by f of u. Okay. Now, there's something missing with this. We aren't taking into account the case where um, our transfer could fail, right? Like if we're transferring, for example, from f of u plus 2 to f of u plus 3 and suddenly it fails, then we'll go back to f of u, right? So we'll use all of those edges a second time. So how do we account for that? Well, we can say that the function t over u and v is equal to this original term we had plus uh, t of u t of u and v multiplied by fail. Okay, so there's kind of a cycle here that we're making, right? That in case it fails, then we use this function again, right? Now, we obviously can't calculate this recursively because there's no base case, but just with basic algebra, first let's replace the fail with the actual probability, okay? So the probability of it failing at some point is 1 minus the probability of it succeeding, right? So it's 1 minus the product of pi from I is equal to u to v minus 1, right? Because those are the probabilities involved in transferring it from u to v. Okay, and using our earlier deduction, we can say that that's equal to 1 minus f of v upon f of u. And so if you replace this the fail in the equation above with this value, then eventually you can reduce the equation to this. The expected time to go from u to v is equal to f of u plus f of u plus 1 plus f of u plus 2 all the way to f of v minus 1 upon f of v. Okay, so yeah, now that we have this formula, how do we solve further? So one observation is that we can think of memory disks as a checkpoint, right? Like once we get from one checkpoint to the next one, then the next stage is independent, right? Because there's no way we'll come back all the way to the very first checkpoint. So we can consider the value of data transfer between the checkpoints individually. Okay, so over here as an example, I'll give you two examples here. So let's say we have this n is equal to 5 case, okay, and we've set up our memory disks at 2 and 4. Okay, so in that case our answer will be t of 0 and 2 plus t of 2 and 4 plus t of 4 and 5. Okay, similarly if we put up disks at 1 and 3, our answer will be t of 0 and 1 plus t of 1 and 3 plus t of 3 and 5. Okay, now given this, how do we find the optimal way to select stations? I propose the following DP. Okay, we can say DP x and y is equal to the optimal expected time for transferring data from station 0 to station y after having placed x memory disks, and the most recent of these memory disks was at station y. Okay, so what it means is that we're basically considering the segment between station 0 and station y. Okay, and within this segment we've placed x memory disks. Okay, and one of these memory disks, the most recent one, was on station y. Okay, and what our DP stores is the minimum possible expected time if we do this. Okay, so DP of 0 0 is obviously 0. Okay, and notice that all non-zeros, like DP 0 of anything other than 0, will always be like infinity. Okay, because it's not a valid case, right? If we're not placing any more what should I say, if we're not placing any more memory disks, then obviously no location other than 0 can have a memory disk, right? So therefore DP is 0 of 0 is equal to 0 and 0 of anything else is equal to infinity, let's say. Okay, then dpxy, where x and y are both greater than 0, is equal to the minimum value of dpx minus 1 k plus the time between k and y. Okay, for all k such that k is less than y. And I'm really sorry for reusing k, guys. Like, I didn't realize this while making the presentation, but um, like in these two lines, k is completely independent of the input variable. Okay. So over here, the minimum value of we need to find for each dpxy the minimum value of dpx minus 1k. So what this means is, um, like, after having placed x minus 1 station, uh, the optimal expected time to reach station k, okay, and our last memory disk for that station k, okay, plus t of k of y obviously means that the time expected time to get from k to y, and we're placing now a memory disk on station y. That's our exit memory disk, okay. So over here we're looking for like sort of the optimal breakpoint k in our dp, okay. So, and then finally dp k plus 1 to n is the answer, okay. And this is just an easy way of implementing it. I know that you have to put down x memory disks, but putting down x plus 1 and taking that as n is the easier way. If you don't want to do that, then you can do dpk, and you can just check all locations and how they work with n. Okay, I'll show you how to do that. So let's try to code this in. Okay, note that this is not the sufficient answer, but coding it in will help us get there. Okay. So we've inputted all our f's, okay? I've already done the input part. So let's just do the dp, okay? So you can say double dp, and it's important to keep it as double, okay? Double dp k plus 2 n plus 1, okay? Now, first, let's set everything else to infinity as I described earlier. So we can say dp 0 as equal to infinity. And infinity here is the carefully chosen value. So f is between 1 and 1e12, and n is between 1 and 1e5. So 1e17 is the max value we can have, and so 1e18 is infinity. Okay, this is important. And dp00 is equal to 0. Okay, so now let's calculate. So int x is equal to 1, x is less equal to k plus 1, x plus plus. For int y is equal to 1, y is less equal to n, y plus plus. And we can say int sorry, not int, we can say dp x0 is equal to 0, just like a basic thing, because that will never change. Okay, now we need to go backwards. Okay, so let's set j as our potential breakpoints. Okay, and we're checking over all breakpoints which one is the most optimal. Okay, now to replicate the cost function where we had found the cost function would be this, right? So to replicate this, I'm storing the numerator in a variable called sum. Okay, sum. Okay, and now we can just say, so initially we can say dpxy is equal to infinity, and now each time we go here we can say dpxy is equal to min dpxy sum plus dpx minus 1 j, right? That's we're following our recurrence given here, right? So we can do this, and then finally we can output the answer. First we need to set the precision. So I think it requires up till 10 to the power minus 6, but just to be safe, we'll do it till 10. Okay. And we can say dpk plus 1 n. Right? So let's just try this on our sample case here. The expected answer is 4. Okay. So it's just taking some time to compile. Just give it a second. Okay, it's giving 6. There must be some error. Let's take a look. Oh, I'm sorry. It should be sum divided by f of x, f of y. Yeah, right. My mistake was that in this formula, I forgot to divide by the denominator. Right, that was the mistake. Sorry. So sum divided by f of y should fix it. Okay. While we're waiting for it to compile, okay, it's done. Yeah, 4. So while we're now let's look at the time complexity, right? If we do this naively, like I just showed you, then the time complexity is order of n squared into k, right? Because these two are n squared, and this is k, right? These are n each and then k, right? So n squared k, right? And the space complexity is nk because of this dp matrix, right? Nk. Now we need to optimize this, right? Because n squared k is something like 10 to the power 11, and that's not feasible. So to make it faster, we're going to use something called divide and conquer DP. Now again, it'll be great if you guys have already read this, but if not, then I'll very mildly touch upon it. Okay. So the requirement for divide and conquer DP is this. Okay. Consider DP A to B and DP A to C. Okay, where B is less than C. Okay, A is less than B and B is less than C. Okay. Now we need to prove that the optimal breaking point being, so for example, dpxy here, our breaking point would be the best j that we found over here. Okay, the index j. Okay, so we need to prove that the optimal breaking point for dpab is less than or equal to the optimal breaking point for dpac. Okay, now how do we do this? To do this, we can use something called the quadrangular inequality. Okay, and this is a common thing used in competitive programming a lot, so it's good if you learn it. Okay, what we need to prove with the quadrangular inequality is that the cost function, which is t for us, t of a and c plus t of b and d, is less than or equal to t of a and d plus t of b and c, where a is less than equal to b, which is less than equal to c, which is less than equal to d. Okay, and intuitively, if you see, what we're trying to prove is that if we take two different cost functions where the range of the function is equal, right? Like it's over the same range, then it's better to have the average size lower than to have one big one and one small one. Okay? That's what we're trying to prove intuitively. Okay? So let's do it like this. Let's define SFI SFI is basically the prefix sums over f. Okay? So S of I is equal to f of 0 plus f of 1 plus f of 2 all the way till f of I. Okay? Now t of a and c is equal to f of a plus f of b all the way to f of c minus 1. Okay, so I've broken that down with prefix sums. Okay, and similarly I've done that for all of the terms in the that I've shown above in the quadrangular inequality, right? All of the terms shown here, I've broken them down over here using prefix sums. Okay, I'm hoping you are comfortable with prefix sums. If not, then please read up. It's a very basic topic. Okay. So after breaking this down, we can move this function, this term to this side and this term to this side, and you'll see that we'll get this, right? S of b minus 1 minus f of a minus 1 less than equal to s of b minus 1 minus s of a minus 1 upon f of c upon f of d. Okay. Now, like it's really basic to evaluate this. You can just cross multiply, cross divide, and cross multiply. So we'll get eventually f of d is less than equal to f of c, right? So this is what we have to prove, and if this is true, then a quadrangular inequality is valid. And luckily, in our input, which I said would help us earlier, is this inequality, right? So this proves that f of d, where d is greater than c, is always less than or equal to f of c, right? Because it's in decreasing order. Okay. So we can use divide and conquer dp. This proves it. Okay. So let's actually code it in. Okay. Okay. Now, the first thing we should do is make those prefix sums, right? I'd use s earlier. I'll just use s again. Okay. So you can say s of 0 is equal to f of 0, and then from 1 to n, we can say s of I is equal to s of I minus 1 plus f of I. Okay. And to get the sum of a range, you can just make a function really quick. Okay. Okay. It's supposed to be double, okay? Because we have to return a real value, so it's very safe to operate for everything in double. Okay. So that's our sum function, and let's just create another function to calculate t. Okay, our cost function. Okay. So t of u and v, as I said earlier, was calculated using this, right? So we can replace this with return get the sum from v minus u to v minus 1 divided by the sum from v to v. Okay. So we have a cost function stuff easily accessible. This is very useful. Now let's actually implement the divide and conquer part. Okay. So instead of k plus 2 n plus 1, let's start the important observation is that to calculate dp xy, okay, or to calculate dp xi where I can be anything, we only need access to all dp x minus 1j. Okay. So to calculate one layer of dp, we only need access to the previous layer. Okay. All the other layers are useless. So how this helps us is that we don't need to store all k plus 2 ones, right? At one time, all we need to do is store a single dp. So we can remove that dimension and reduce the space complexity a lot. Okay. And we can remove the second dimension from everywhere. Okay. Fantastic. Uh, Now inside we need to store like another array temporarily, which will temporarily store our dp, and after we're done calculating it for this layer, we'll copy over this to dp. Okay. So let's set a of 0 is equal to 0 as we did earlier. Okay. And let's create a stack here so we can process our divide and conquer dp. Okay. The stack will be in this form. Okay. It's basically a pair containing two pairs. Okay, of integers. Okay. Now, I'll just tell you how the like how the stack is structured. Just give me a second, okay? So int l is equal to st dot first dot first, int r is equal to st dot first dot second, int opt l is equal to st dot second dot first, int opt r is equal to st dot second dot second, okay? And int cur is equal to mid lr, okay? Sorry, st dot top. Okay. And just to be safer, let's just put this in right now. Okay. St dot not push, sorry, pop. Okay. So this is enough. Now, so what this means is L to R basically means that like we calculated DP in a divide and conquer way, right? So right now we need to calculate DP for everything in the range L to R. And if you know divide and conquer, you should know what the optimal ranges are. Okay. It basically means that for everything between L to R, the optimal value will lie between optel and optar. Okay, the optimal breaking point will lie between optel and optar. Okay, so the first thing we should push is we need to find it for everything between 1 and n, and the optimal values could be anything between 0 and n minus 1. Okay, the optimal breaking points. Okay, it can't be n obviously because there's nothing more than like beyond n which would break earlier. Okay, and yeah, and we don't need to calculate dp, we don't need to calculate dp0, right? Because we already set it to 0, right? So now we need to keep two variables. First stores the optimal value that we've currently reached, and the second stores the optimal index. Okay, the basically the optimal breaking point. Okay, so initially we set the index to 0, and we find the optimal value as t from 0 to cur. Okay, now let's go over all the possible breaking points. Okay, we can say it's minimum of cur minus 1 and optel to min minus cur minus 1 to optel, and it's less than equal to min of cur minus 1 and optar. Okay, and we can do I plus plus. Then we can say that the cost of doing it, of using this as a breakpoint, is equal to dp of I plus the cost, which is t, from I to cur. Okay, if we say if this cost is less than our current optimal cost, which is optval, then let's set cost optval is equal to cost, and let's set this as the optimum index I, the breaking point. Okay, so this is our calculation for dp of cur done. So you can set a of cur is equal to optimal value. Okay, and then we can say if l is not equal to cur, then we need to recurse on the left side, right? So we can say st dot push. Um, so what are the bounds we need to do on? We need to do it on l to cur minus 1. Okay, and the optel can be the range for opt is optel to opt-end. Okay, and similarly if r is not equal to cur, then we need to push cur plus 1 to r. as the range where we need to calculate. Sorry. And then we need to push as the range where our optimal index can lie, opt-in to opt-out. Okay. Uh, yeah, this should be sufficient. And then we just need to copy everything. Okay. So we just need to do DPI is equal to AI. Okay, at the end of our divide and conquer. And obviously we need to replace this with DPN. So there's an issue here. Okay, that's solved. So let's try this out. Huh? It takes so much time. Yeah, so this is 4. So let's go ahead and submit this. If it's wrong, then we can do some debugging. Okay, and submit. So while that's running, uh, with divide and conquer, the time complexity of this was order of n k log n. Okay, which comes out to something like 10 to the power 7 or something like that. Yeah, about 5e7. Okay, which is very fine, and the space complexity is order of n, which is perfect. Okay. Now, did you also know that CodeChef conducts live courses on Unacademy? Okay, these courses range from basic topics like Introduction to C++, Java, STL, basic data structures, etc., all the way to advanced things like segment tree, graph theory, dynamic programming, etc. Okay, these courses are taught by experts who are ISPC World Finalists, IOI medalists, Facebook engineers, Google engineers, and so on and so forth. Okay, they're very pro. So, um, to look at this course, all you need to do is either register on the app or register on the Unacademy website, unacademy.com, and select competitive programming as your goal. Okay, we also offer a plus subscription on which we offer things like large problem sets topic wise based on what you learn in class, and also we have 7-star and 6-star programmers as teaching assistants who can help you with your doubts before, during and after all the sessions. Okay, and if you register for plus right now, then you can use my referral code agu to get a 10% discount on plus. Okay, so don't miss the opportunity to kickstart your competitive programming journey. Okay, so let's take a look at our submission, and we got the correct answer. Okay,